Welcome to lecture, I think it was like 28 or something like that, 29.
That's it? So far?
That's it? I'm not sure.
So many. Okay.
So, a bunch of people are not here today. Whatever. Today's Thursday. On Tuesday, we solved the area problem. That's basically what we did, right? And we ended with this process of finding the areas of the curve by taking n rectangles and letting the number of rectangles go to infinity. So then there was some homework. I think it was pretty short, right? It was like 5 problems. Should we do one? Let's go over one problem to make sure we're good.
I actually did
55.
55? Did it go okay?
Yes.
Basically? Okay, let's do it. It'll take us like, I don't know, 5 to 10 minutes. 55 is this problem. I believe the function is something like x squared minus x cubed, right? So f of x is x squared minus x cubed, and we're doing this on the interval from -1 to 1. So, and the goal is find the area. All right, in my opinion, this process is only worth doing and makes sense if you're actually thinking about what you're doing. And so I think the process of drawing the picture and drawing the rectangles is like crucial. So if we try to make a picture of this, let's see, we can factor out an x squared. So that's 1 minus x, and actually that's like negative x squared x minus 1. Okay, so I know what this function looks like then. From experience, it's going to be a cubic, leading coefficient negative, root at 1, and double root at 0. So it's going to be some kind of thing like this. Yeah? Yeah. Okay, so if I go to graph this, let's see, at 1 it's going to be 0, at 0 it's going to be 0, and at -1 it is going to be 2, right? And it's going to be an upside down cubic, so it's going to have end behavior like this. So I got a nice big graph, double root here, something like that. Alright, and the goal now is to find the area between this curve and the x-axis between x is -1 and x equals 1. So I'll just very lightly in green just shade the area it is that we are trying to find. All right, and that looks like about, I don't know, to me it looks like about 1 maybe if you smush all that together. Just ballpark. Okay, so we have an option of dividing it up into rectangles using either LRAM or RRAM. I recommended last class that we just always use RRAM because for that sort of technical reason, just the algebra turns out easier because the ith rectangle is determined, is such that you've moved over I times by the width. And okay, what is the width? If we're going to use n rectangles, then what is delta x, the width of each rectangle? 2 over n. 2 over n. Yeah, the whole interval is with 2, so each one is with 2 over n. Okay, so I'm going to start drawing in some rectangles. So there's a rectangle, there's another one, there's another one. Etc. And I'll just kind of put like dot dot dot, and we'll go over like the last rectangle is actually going to be flat. So I'll draw the second to last one in like that. Okay, so now you have to find the pattern. If delta x is 2 over n, then this value right here is like -1 plus 2 over n, and then this next one would be -1 plus 2 times 2 over n. It's just how much. This is like cool. I mean, I know we did this last class. And then this is -1 plus 3 times 2 over n. Etc. Etc. Okay, dot dot dot, and until one good way to make sure that you got it under control is by the time I get to the nth rectangle, I will have moved over n times. So this last the right-hand endpoint of the last subinterval should be -1 plus, and now it should be n times 2 over n because I've moved over 2 over n times. And if you multiply that out, you get 2, and -1 plus 2 is 1, so it's like all matching and making sense. Cool? Seem cool? Okay, and then you just have to find out what these points are. So, well, this would just be -1 plus 2 over n, comma, f of that. And this is -1 plus 2 times 2 over n, comma, f of that, et cetera, et cetera. And so we can write out what S is, the sum of the areas of all the rectangles. It's going to be, well, the first rectangle is going to have width 2 over n, and height f of -1 plus 1 times 2 over n. The second rectangle will have width 2 over n and height f of -1 plus 2 times 2 over n. Plus, and et cetera, et cetera. Eventually we get to the nth rectangle, and the nth rectangle will be 2 over n times f of -1 plus 2 plus n times 2 over n. And maybe you don't need to write that step, but it is helpful, and thus I can express this in sigma notation. In sigma notation, this is going to be 2 over n sum from I equals 1 to n of f of -1 plus I times 2 over n. Alright, raise your hand if you got this far. Okay. That's like the important part, in my opinion, is the ability to understand what's going on, to make a picture, to understand the process, to draw the rectangles, to find the pattern, to figure out what delta x is, and to get the right sigma notation. From this point on, it's just like cranking it out and like trying not to mess up. So, alright, when we go to do it, we're going to have 2 over n times the sum from I equals, now I'll go a little faster, sum from I equals 1 to n of, well, the function is x squared minus x cubed. So it's going to be 2 over ni minus 1 squared minus 2 over ni minus 1 cubed. And I think, in my opinion, the simplest thing to do is to expand everything out and combine like terms inside the sigma. So this will be 4 over n squared I squared minus 4 over n I plus 1 minus, I'm going to use the binomial theorem here, assuming I can do that without messing up. It's going to be like, so it'll be like a cubed, so 8 over n cubed I cubed, minus 3a squared b, so 3 times the square of that, so that would be 12 over n squared I squared. Stop me if I mess up.
But that's I cubed, right, on the first term.
I cubed, yep, thanks. Plus 3ab, so that's 6 over ni plus 1. Boom. Okay, awesome. So now I'll just combine all these guys together into one expression. That seems like a good idea. So that'll be -8 over n cubed I cubed. 12 and 4 is plus 16 over n squared I squared. Minus 10 over ni. And then
Is that a -1?
that should be a -1. Yup. Yup. Thanks, Ethan. That's +1, so the biggest one ends up being +2. Alright, it's really not so bad, but you do have to kind of be careful and not like drop the baby or whatever. Alright, so now if we split this up, I get -16 over n to the 4th times the sum of the cubes. This is the way I think it makes most sense to do this. Plus 32 over n cubed sum of the squares minus 20 over n squared, the sum of the i's, plus 4 over n times the sum of the ones. Alright, and now it's just a matter of using these formulas one at a time. It's -16 over n to the 4th times n plus 1, 2n plus 1, no, wrong form. N squared, n plus 1 squared over 4, plus 32 over n cubed. Now this is n plus 1, 2n plus 1 over 6, minus 20 over n squared, n plus 1 over 2, plus 4 over n times n. Cool, I feel like that's all right. And now we just do it. Some cancellation happens, and this is canceled, it becomes a 2, that becomes a 4, that becomes a 16, becomes squared, 10, like that. Alright? So my final expression is negative 4 times n plus 1 squared over n squared plus 16 thirds times 2n squared plus 3n plus 1 over n squared minus 10 times n plus 1 over n plus 4. Whole lot of work to get this big, complicated expression all involving a bunch of n's. And you should be able to articulate what this actually means, right? I mean, like, what is this? Not the limit yet. What is this thing, Yal?
It's the approximate area when it's split it up into n bars by r and n is on the
Yeah, that's right. It is the approximate area. It is the approximate area under the curve. Specifically, it's the area under curve as approximated with n rectangles for this function on this interval using Rm. So is everyone okay with that? And then, of course, if we want to know the exact area, we take the limit as n goes to infinity of this whole thing. And if you write it like this, it's pretty easy to do. This is going to be, if we take the limit as n goes to infinity of this whole thing, we get negative 4 plus 32 thirds minus 10 plus 4. And the 4's cancel, so that's 32 thirds minus 30 thirds, so my final answer is 2 thirds. Pretty awesome. Where's any of you got exactly 2 thirds? Like most people? What happened? Those of you who didn't. Magna, welcome. Sameen, welcome. Where's my sweet frog? Okay, wait, Eric, what happened?
Well, I didn't.
Oh, you didn't do the homework. Okay, good. So 100% of the people who tried the problem got it right. 100% of the people who got the problem right got it right. All right. So good. Oh, so many more people. Great. Can I? Wait, for real? Why'd you guys come back?
Because we didn't want to miss this.
Yeah.
Whoa, they revealed all the text. There's a text.
Oh, it's because Ethan told you to come back?
No, it says,
or
where
you were
are
gonna
you?
you were gonna come back anyway.
We were down the stairs when he sent that.
Oh yeah, I just said.
It was, are you coming to math? We're coming up now.
Okay. Good. Can I have this homework from you guys? Anyone who shows up today and hands in the homework now will get bonus points.
Oh, seriously?
Justin,
Really?
Incomplete.
Wait, seriously? You marked that on here?
Yes. Arun, can you grab a red pen and write +5 bonus on the top of all of these homework?
+5 bonus? Yeah. Yeah. +5 go to the test, actually. We should get like bonus test by day.
Alright, good. Anything else we can do that's like
yeah, there's like no
fun or cool that would make the other people jealous who weren't here?
Go outside. Go outside.
Yes, go outside.
Yes, go outside. Yeah, go outside.
Line up and
No,
pretend
we're
to
not
be
going
a
outside.
Oh yeah. Go to Elias' house. Go to Elias' house. Oh yeah, let's all just go up at Elias' house today.
I got nothing. I can't think of anything.
Wait, can't we just go outside?
No, we're not going outside. We're working hard. The whole period. Nothing else.
Let's call this thing to us.
No, we're definitely working hard the whole period starting now. That's the whole point of this whole thing, is that we have like a lot of work to do. All right.
really easy method to do
Oh, we should do tons of textbook work so that they have to do all the textbook work at home.
Yes.
I was looking for something that was a little bit more like just like stupid that takes no time.
Why do they miss?
Tell us a story.
Give us food.
Yeah.
Oh, that's a thing we can do. Yeah, okay.
Bobby.
I have Milanos.
Keep those
Milano party. 4, 5.
Oh yeah.
Milanos.
16.
Should have
Is there anyone who doesn't want one?
Yeah. What?
Okay, good. Then I think they used to put 15 in here, but I don't know. Times are tough.
We're just gonna fight to the death.
I think there are 15 Milanos in here, so everyone gets a Milano. Hopefully, there's enough for everyone. Is this relatively clean?
I don't know.
And that Chipotle. Who else is
I kind of want one, but I'll wait.
No.
No?
No. You don't deserve it.
I could if I wanted to.
Wait, I thought these-
Yeah, they're good.
Oh, there weren't.
Wait, why are you recording this?
Yeah. Who's gonna take the last one? I'm interested.
Really?
I could eat whatever.
Did everyone get one? Arun, you want one?
You can have it.
No, it's all you.
I'll take it.
All right, good. So, math. Good. All right. So check it out. Uses. We've mastered this process now, I think, of finding the area under a curve. Except that's actually a total lie. Because I can easily come up with problems where things suddenly go wrong, and that's what I'm going to do right now. So here is a problem. F of x equals root x. And I would like to find the area under this curve on the interval 0, 1. Okay, go. And if you have some brilliant idea of how to do this,
I'll just take off the chair.
kind of just keep it to yourself.
I only need one chair.
Yeah, go, just go, start, fast.
So we're supposed to keep it to ourselves?
I just want to go to the chair.
Seriously?
It's not good for you. I'm helping you.
Draw a picture, split up the rectangles, draw some rectangles, do what you need to do, and then probably you will start to get stuck, and then you will cry.
When you need to find the top.
She said, let's hear she said okay, but.
Really?
The wheels?
She kind of doubt it. They seem like.
Oh, she says we are coming 3 minutes ago.
No, they decided not to come. No, they decided not to come.
What?
Fx equals root x on the interval 0, 1. How's it going? Raymond, what happened? What happened?
Oh, I couldn't do it because I wasn't here last class, so I have no idea.
So you pretty much have no idea what's going on. Did you watch the video?
Not yet, no.
Probably you should do that like before the following class, so as to not have the problem. Yeah, Buses, what happened?
We don't know the sigma formula for root x.
Wait, but we, from 0 to 1, can't we like still
Wait.
Wait, what
Maybe,
is
yes.
happening?
But it's okay.
like my sperm?
What? Okay. Yeah. So yeah, let's just naively just like hope for the best and just push on. That's
That's what mathematicians do.
that's what people do. They just like try crap and see what works. So let me just try the same old until it doesn't work. I have no reason to stop doing that. So I will. This is 1. That's like the 0.11 or whatever. And then I am going to do the same thing that we have been doing. I'm going to attempt to find the area under this curve. Seems like RM is a good idea because, whatever. And so I will split this up into,
Do I get $2?
I will split this up into n rectangles. What's delta x, the width of each rectangle? 1 over n, of course, because the total width of the interval is 1. There are n rectangles, so delta x is 1 over n. So if I start to do this, I have my first rectangle here. That's at like 1 over n. I have my second rectangle here. That's like 2 over n, 3 over n, etc. 3 over n. And then we scoot over to the last rectangle, and then that would be like n over n. Is everybody with me? Yeah. Okay. So far seems fine. Same old. But then we go to actually do it. Well, if we go to actually do it, can I go straight to the sigma now? We're like building skills. We're skipping like another step every time. So if we go straight to the sigma, this is going to be the width of each rectangle is 1 over n times the sum from I equals 1 to n of, and what is the height of the ith rectangle? Yeah, it's just going to be f of just I times 1 over n. But this is bad because what we have now is 1 over n times the sum from I equals 1 to n of like root I over n. Uh-oh.
Why the bed?
I don't know.
Oh, right.
Yeah, I feel like we just kind of can't do it. I can pull out the root n, I can do that. I can write this as 1 n root n times the sum from
Can I
I
get
equals
$2?
1 to n of root I. You don't get credit for mine.
What? I got one to live in a spot.
Actually, maybe you should get extra credit for mine.
Yeah.
Anyone, $10 if you get Mateo. I mean.
He's been gone.
Okay, all right, wait, hold on. Stay.
Yo still wants his money.
Yeah, that's pretty.
Okay, wait, hold on. Well, we'll pause the camera in a little bit and we'll do it. All right, so what happens? What happens? Those of you who have been here for the last 20 minutes, what happened? Yeah, we're just stuck. I mean, there's nothing logically wrong with this procedure at all. But we get to a certain point and we're just stuck. I do not have a formula for, unfortunately, for the sum of the first I radicals, and I don't feel like there's going to be one, at least not a pretty one, right? I kind of don't really know what to do, and I begin crying. I don't know how to draw tears. So actually what this does is to reveal the shallowness of our entire procedure that we have. All of this, we were 5 minutes ago, we were so confident that we had solved the area problem, but as it turns out, we've solved only a very particular kind of area problem. What?
I texted $10.
Okay, good, Mateo, have a seat. Have a seat over there. Okay, so what kind of functions can we, we haven't, it turns out that we really haven't solved the area problem. What have we solved? What can we do?
Polynomials.
Yeah, polynomials. We're not allowed to talk for the next like 2 weeks though. I already know everything. It's like not fair. Yes, it turns out upon reflection, it turns out that we actually only know how to find the area under polynomials, right? Because only polynomials reduce down to these happy summation forms. Is everybody kind of with me? All right. So now okay, we're going to solve this problem now, and we're going to solve this problem with a wild and crazy solution, not your cool solution that you have. I don't think. We're going to talk about that at the end. Here's our solution. Our solution to this problem is something you probably never would have thought of in a million years. Subintervals of unequal widths. Subintervals of unequal widths. Alright, this is actually kind of awesome. Here is what we're going to do. So first I'll redraw the picture. And yeah, square root function. Okay, now I'm going to do the following crazy thing. I am going to let my, well, and maybe you can actually come up with this yourself, because what I want to do is that what I need to do is I need to like rig this up in some kind of a way such that this like radical won't be here, right? How do you make a radical disappear? Yeah.
Square stuff.
You square stuff. Okay, but I can't just go squaring things
go
just because
like-
I feel like it.
So you just choose widths where they have like perfect square roots.
Yeah, kind of, right? She just says, hey, let's set it up in such a way that the only kinds of numbers that we ever plug into the function are numbers which are perfect squares. And thus, the radical, like, kind of disappears. Okay, but in order to do that, I have to do weird things, right? So watch this. My first subinterval is going to be here at 1 over n squared. And following Emma's advice, where should the right endpoint of the second thing be? Maya. Yeah. Wait, Maya, are you in this period? You're in 9th period, right?
I don't want to be here for that, so.
But you already saw all this yesterday, right? Yeah, so you probably shouldn't say anything. All right, good. So 4 over n squared. So that's like kind of cool. And then what should the next one be? 9, yeah, 9. Now I'm going to go out to 9 over n squared, and I'm going to draw a rectangle over here. All right, and then I'm going to put a dot, 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 and then eventually I'm going to have my last rectangle, which, contrary to the picture, will actually be the largest one of all, right? Because they keep getting wider as I go out. And well, actually, if I'm following this path, well, okay, hold on. Let's start. I'm going to introduce to you now like a new notation, which our book uses. It says let C sub 1 be the right endpoint of the first subinterval. In other words, C sub 1 is 1 over n squared, the right endpoint of the first subinterval. So what's C sub 2? 4 over n squared. What's C sub 3? 9 over n squared. Is this all making sense, everybody? Yeah. Alright, so what is the formula for C sub I, the right endpoint of the ith subinterval? No, in general, I
squared over n squared.
Yup, I squared over n squared. Okay, cool. So I'm introducing, this is my way of introducing this this weird kind of pattern. It's a weird way of splitting up this interval into subintervals. And of course, I need this to be 1, right? So if I need this to be 1, then like how many rectangles? Which rectangle is this? Yeah, this must be the nth rectangle, right? Because I need C sub n to be like n squared over n squared, which is just 1. So this is like n squared over 1, so this is the nth rectangle. Okay, that's kind of cool. Let's investigate this a little bit further. I'll now introduce a new notation. I can't use delta x anymore because delta x assumed that the width of each subinterval was constant, but now they're all different. So let's let delta x sub 1 refer to the width of the first subinterval, which is what?
Which is 1 over n squared.
Which is 1 over n squared, yeah. That's the width of the first subinterval, cool? Okay, and just from looking at it, what is the width of the second subinterval? So, yeah, this is just like 3 over n squared, right? This is just doing subtractions. Everybody cool? I'm gonna go kind of fast because like whatever, just keep it moving. And delta x sub 3, the width of the third subinterval is
5 over n squared.
5 over n squared, etc., etc. Okay, so now what I would like to do, Cindy, you cool?
Yeah.
What I would like to do now is come up with a formula in general for the width of the ith subinterval. How'd you get that, Karisma? Look at it, duh, pattern? Yeah. Okay, so Karisma says look at it, duh, pattern. He says, all right, it's like 1, 3, 5, blah, blah, blah. It's just like the odd number, so it's like 2i minus 1, right? Okay, that's cool, and definitely that's correct. But I would like to do it a little bit more rigorously by actually using the definition. So, so the width of the ith subinterval is
5 plus
The difference between.
kind of, yeah.
The difference
It's like
between
I
C
squared
and
minus-
Cn minus 1.
Yes.
Or Ci and Ci minus 1.
Yes. That's pretty much what you said, right? The width of the ith subinterval is the difference between the right endpoint of the ith subinterval and the left endpoint of the ith subinterval, which is in fact just the right endpoint of the previous subinterval. Everybody cool with that? And so now I can just compute this by formula. The right endpoint of the ith subinterval in general is I squared over n squared, and the left endpoint in general is, what is that going to be? Oh, like this, right? I minus 1 squared over n squared. And if we just like do that out, we get, I squared minus 2i plus 1 over n squared. And so that is 2i minus 1 over n squared. So it turns out our calculation directly by definition is the same as what we would expect just by looking at the pattern. Okay, so this is pretty cool. I have a formula for the right endpoint of the ith subinterval. I have a formula for the width, and the widths are all different. Now's the time to maybe have a little conversation about other things that are going on here. So what happens as n goes to infinity? You guys kind of see what's going on here? It's like the rectangles are growing wider and wider and wider for a particular n. But then what happens when you let the number of rectangles go to infinity? What's happening to the widths?
They go to
The widths go to infinity? The widths get smaller, right? Because what's happening as n grows,
Oh.
right? As n gets bigger and bigger, do you guys feel this 1 over n squared getting really, really close to the origin? But so does 4 over n squared. As n gets bigger and bigger, that's also getting close, right? So they're all actually kind of like weirdly, it's like there's this weird kind of double growth process in the sense that for any particular n, the widths of the rectangles get bigger and bigger, but if you just let n get really big, then they're all sort of still shrinking. And in fact, I can just show that that is true, right? Just by looking at that expression, right? As n goes to infinity, what can I say about delta x sub I? What does 2i minus 1 over n squared do? This goes to 0, right? Take any particular I, like, I don't know, take like the 17th rectangle or something like that, right? If I look at the 17th rectangle, as n goes to infinity, its width is getting smaller and smaller. Okay, so that's something that's really crucial here, which is that all these rectangles are becoming infinitely thin as we let n go to infinity. One more thing, what's the widest rectangle? The last one, right? And actually, what is the width? What is delta x sub n, the width of the widest rectangle?
1.
No, careful. It's not going to be 1. The last one would be the whole thing, right?
C, whatever the last
Yeah. Can you just plug it in? We can just plug in n for I in the formula for the width of the ith subinterval, right? That's what I'm doing. I'm just plugging that. This is going to be 2n minus 1 over n squared. Okay? So even the widest subinterval is going to have width 2n minus 1 over n squared, and thus, what happens as n goes to infinity? What happens to delta x sub n?
0.
That's also going to 0, right? That expression goes to 0 as n goes to infinity. Okay, so basically, my comments here are that this method is legit. I have n rectangles. Even though the rectangles are all of unequal widths, as n goes to infinity, they're all still shrinking to be infinitely small. And so this method just succeeds. It solves our technical problem. If you didn't see it before, you'll see it now. So do the problem. Find the total area. And maybe I'll kind of start us off together. I have to add up a bunch of now. Each time I said I would skip a step, so now I'm going to go straight to the sigma. So I want to sum up a whole bunch of things. I have n rectangles, and what I would like you to do right now is to write me an expression for the area of the